Hey there, and welcome to this explainer. Today, we're doing something really cool. We're decoding the secret language of matter. We're going to connect the invisible microscopic rules of particles to the very visible macroscopic lines you see on a graph. If you've ever stared at a heating or cooling curve and just seen a bunch of random zigzag lines, well, you're in exactly the right place. Because by the end of this, you'll be reading those graphs like a pro. Okay, let's dive right in.
Here is our roadmap for today. First, we'll cover the kinetic molecular theory basics, then we'll define phase changes. After that, we're decoding the heating curve, followed by the cooling curve, and we'll wrap it all up with our exam-ready key takeaways.
All right, Section 1, Kinetic Molecular Theory Basics, basically the rulebook of matter.
Okay, so these points right here, they're the absolute core rules of the physical world straight from your exam guidelines. The kinetic molecular theory, or KMT, tells us that matter is made up of really small particles, and those particles are in constant motion. As they zip around, they collide and exert pressure, and there are forces of attraction between them. But here is the golden rule you absolutely have to remember. The temperature of a substance is simply a measure of the average kinetic energy of its particles. When you change the energy of those particles, a phase change might just happen. Keep that direct connection between temperature and kinetic energy in your mind. It's literally the key to everything else we're going to talk about today.
Moving on to Section 2, defining phase changes, getting the exact vocabulary down.
Let's start with the boiling point. Now, the exact wording here is absolutely crucial for CAPS. Boiling isn't just about a liquid getting super hot, right? It's actually the precise temperature of a liquid at which its vapor pressure perfectly equals the external or atmospheric pressure. If you're asked to define this in an exam, that specific balance of pressures is exactly what they're looking for.
Next up, we have the melting point. Simply put, this is the exact temperature at which a solid, if you give it sufficient heat, becomes a liquid. It's basically that threshold where those tightly packed solid particles finally get enough energy to overcome their rigid forces of attraction and start moving much more freely as a liquid.
And on the flip side of that, we have the freezing point. This is defined as the temperature at which a liquid changes to a solid by the removal of heat. You take away the heat, the average kinetic energy drops, the particles slow way down, and those attractive forces pull them right back into a fixed, solid structure.
Section 3, decoding the heating curve, or as I like to call it, reading the invisible.
When we look at a standard heating curve, like the ones you'll see in Sayavula, you've got temperature in degrees Celsius on the y-axis and time in minutes on the x-axis. At first glance, it kind of just looks like a staircase going up, but every single sloped incline and every flat plateau is actually telling you exactly what the molecules are up to. As we move from left to right across the graph, we are constantly applying heat to a solid substance, let's say a block of ice, and watching it transform.
But here is where we hit a really fascinating mystery. Notice those completely flat lines? If we're constantly heating this beaker over a Bunsen burner, pumping more and more heat energy into it as the clock ticks, where on earth is all that energy going if the temperature isn't even budging?
Well, here's the secret to unlocking the whole graph. It's all about the difference between the slopes and the plateaus. On those sloped lines, the temperature goes up. That means the heat energy is making the particles move faster, which increases their average kinetic energy. But on the flat lines, the temperature is perfectly constant. As a substance is melting or boiling, the heat energy temporarily stops increasing the kinetic energy. Instead, all of that heat energy goes entirely into breaking the bonds between the molecules so the substance can change state. Once those bonds are broken and the phase change is 100% complete, the temperature finally starts to climb again.
All right, Section 4, Decoding the Cooling Curve. Basically, we're just reversing the process.
Think about a standard cooling curve. You'll instantly notice that exact same pattern of slopes and flat plateaus, but this time we're heading downwards. This is exactly what happens when you take a gas, like super hot boiling water vapor, and slowly, steadily remove the heat over time.
As we walk down this graph step by step, the whole sequence unfolds. First, on that downward slope, the gas cools down. The average kinetic energy decreases as the temperature falls. Then boom, we hit the first plateau, condensation. The temperature stays totally constant while the gas turns into a liquid. Why? Because the particles are forming bonds. Once it's completely liquid, it cools even further on the next slope, lowering that kinetic energy again. And finally, we hit the freezing plateau. The temperature locks in and stays constant while bonds form to create a rigid solid.
And finally, Section 5, Exam Ready. Let's look at the key takeaways.
So, to check all the boxes for your CAPS requirements, here's what you absolutely need to master.
You've got to be able to interpret and draw both heating and cooling curves right from experimental data. You need to be able to use the kinetic molecular theory to explain exactly why lines are sloped or flat. Remember, it's all about kinetic energy versus breaking and forming bonds. You've also got to state those precise definitions for melting, boiling, and freezing points exactly as we covered them. And finally, if you're given a random temperature along with a substance's melting and boiling points, you must be able to confidently declare whether that substance is currently a solid, a liquid, or a gas.
And that brings us to the end. Now that you can fluently read this secret language of particles and energy, you are absolutely ready for those exams. The zigzags on those graphs aren't just random lines anymore. They're the literal story of matter changing state right before your eyes. Think about it. If you can decode the invisible forces of molecules on a simple graph, what other hidden mysteries of the physical world are waiting for you to uncover? Thanks so much for joining me on this explainer, and keep questioning the science hidden in the world around you.